America has a lot of natural gas. That is not the same thing as being able to ship energy across an ocean. A gas well in Texas cannot heat a factory in Germany. A shale field in Louisiana cannot become a cargo by itself. Before American gas can move through global trade, it has to pass through a narrow industrial layer on the coast. That layer is the LNG Export Terminal. It is easy to miss because the word terminal sounds ordinary, like a dock or a warehouse. But an LNG terminal is not just a place where ships park. It is the machine that turns domestic gas into international supply. The gas arrives through pipelines. It is treated, compressed, cooled, stored, and finally loaded onto a specialized ship. Only then does it become a cargo that can cross the Atlantic or the Pacific. That is the hidden part of America's gas power. The country did not become a major LNG exporter just by drilling more gas. It became a major exporter when it built the coastal machinery that could turn gas into liquid and move it onto ships. The first large-scale lower 48 export facility was Sabine Pass. In 2016, as Sabine Pass began exporting, the United States became a net exporter of liquefied natural gas. Before that moment, the shale boom was mostly a domestic story. After it, American gas could enter a global market in a different way. This is why LNG terminals matter. They are not just energy infrastructure. They are conversion points between two worlds, inland gas fields and overseas demand. And because there are only so many of them, because they are expensive, regulated, exposed to storms, connected to pipelines, and slow to replace, they are also choke points. The question is not simply how much gas America has. The question is, how much of it can pass through the terminal? Liquefied natural gas begins with a physical trick. Natural gas is cooled to about -260 degrees Fahrenheit. At that temperature, it becomes a liquid. In liquid form, it takes up far less space, which makes it possible to store and ship across long distances. That sounds simple in one sentence. On the ground, it is a huge industrial process. The gas has to arrive at the terminal through supply pipelines. It has to be treated and processed before it can be cooled. The terminal needs liquefaction trains, storage tanks, marine berths, loading arms, control systems, safety zones, and ships designed to keep LNG cold during ocean transport. An ordinary port cannot do this. A container terminal cannot suddenly become an LNG export plant because a ship is waiting. A grain elevator cannot load liquefied gas. A crude oil dock cannot automatically replace a liquefaction train. The export terminal is the piece that makes the cargo possible. That is why the machinery matters. The tanks are not decoration. The pipes are not background. The loading arms are not just another dockside detail. They are the chain of steps that changes the value of the gas. Before the terminal, the gas is part of the North American pipeline system. After the terminal, it can be sold as a seaborne cargo to customers thousands of miles away. This is the core of the LNG story. The terminal does not create the gas. It changes what the gas can do. And that is where the bottleneck begins. If the pipelines cannot deliver enough gas, the terminal cannot load what it does not receive. If a liquefaction train is unavailable, the berth alone cannot produce cargo. If the storage tanks, safety systems, or loading equipment are constrained, the ship waits. If regulatory approval is not in place, the project cannot simply appear because the market wants more supply. In LNG, energy power is not abstract. It has bolts, valves, steel, permits, ships, and a coastline. The American LNG export system is not evenly spread across the country. It is heavily concentrated on the Gulf Coast, especially in Louisiana and Texas. That concentration makes sense. The Gulf Coast is close to major gas supply basins, pipeline networks, industrial ports, deep-water channels, and a long history of energy infrastructure. But concentration also creates a specific kind of dependence. FERC lists existing U.S. LNG export terminals that include Sabine Pass, Corpus Christi, Cameron, Freeport, Calcasieu Pass, Cove Point, Elba Island, and Kenai. The list shows something important. The system is national in consequence but coastal in physical form. American gas may begin far inland, but when it becomes LNG, the decisive layer is often a narrow strip of industrial shoreline. That shoreline is where ships can reach the plant. It is where pipelines meet marine berths. It is where storage tanks sit near navigation channels. It is where storms, port traffic, safety rules, dredged waterways, local communities, and international buyers all meet the same physical system. This is different from a normal export story. If a factory makes furniture, it can often choose between trucks, rail, containers, and multiple ports. LNG is less flexible. The cargo itself requires a specialized terminal and a specialized ship. The result is a system with enormous reach but a narrow exit. Sabine Pass in Louisiana became the symbol of that shift because it opened the lower 48 export era. Corpus Christi in Texas became another major Gulf Coast example. Cameron, Freeport, and other terminals added to the same pattern. American gas moving through a small group of coastal machines. From a distance, this can look like abundance. More terminals, more tanks, more ships, more exports. Up close, it looks more fragile. The export system depends on specific places doing specific things correctly day after day. That is what makes it a choke point. To understand LNG exports, it helps to stop thinking of a terminal as a location and start thinking of it as a machine. The machine has inputs. Gas has to arrive from the pipeline system. It has to match the requirements of the plant. It has to move through equipment that prepares it for liquefaction. The machine has a cold heart. Liquefaction trains do the work of cooling the gas into liquid. This is not a warehouse step. It is a major industrial process that requires specialized equipment, power, controls, and maintenance. The machine has storage. LNG needs tanks that can hold the liquid safely at cryogenic temperatures. Those tanks are part of the terminal's ability to keep cargo moving even as ships arrive and depart on schedules. The machine has a marine side. LNG carriers need berths, loading arms, tugs, safety zones, trained crews, and procedures. A ship is not just pulling up to a fuel pump. It is connecting to a highly controlled system, and the machine has rules around it. LNG export terminals require federal authorization and review. DOE export authorization and FERC siting and construction review are part of the process for interstate natural gas facilities. Safety regulation also matters because these are coastal industrial plants handling cryogenic fuel near waterways and communities. That combination makes terminals powerful. It also makes them slow. You cannot build one by wishing for more exports. You cannot swap one in like a spare part. You cannot move it inland when storms threaten the coast. You cannot turn every port into an LNG port because the equipment, approvals, pipelines, storage, berths, and safety systems are specific. This is why the visual details matter. The loading arms show where the ship becomes part of the plant. The storage tanks show that cargo has to be held before it moves. The pipe racks show how much industrial routing is needed before gas reaches the vessel. The inspection footage shows that this is not just commerce, but regulated movement through a hazardous energy system. The terminal is a machine. The ship is the output. When demand rises, the simple answer is always, build more. For LNG, that answer is technically true and operationally slow. New U.S. capacity additions in the mid-2020s include Gulf Coast projects such as Plaquemines LNG and Corpus Christi Stage 3, with Golden Pass expected to add more capacity when completed. But the existence of new projects does not mean capacity can appear instantly. An LNG terminal has to clear approvals. It has to line up financing, engineering, contractors, steel, modules, turbines, compressors, tanks, marine equipment, pipeline connections, power needs, and buyers. It has to be built in a coastal environment where weather, shipping channels, labor, local concerns, and safety review all matter. That is why the construction footage is important. Modules moving through a yard are not just construction scenery. They are evidence of the scale. A liquefaction project is not a small building. It is a layered industrial system where each piece has to fit into the next. There is also a timing problem. Energy markets can move quickly. A war, a cold winter, a supply disruption, a price shock, or a policy shift can change demand in weeks. LNG terminals do not respond on that schedule. Even when a project is already underway, capacity comes in stages, through trains and phases and commissioning. That gap between market speed and construction speed is one of the main reasons LNG terminals matter as choke points. The United States may have large gas resources. It may have companies willing to build. It may have foreign buyers willing to sign contracts. But the export system still has to pass through a sequence of physical and regulatory gates. That makes the terminals strategic. They are not just places where energy leaves the country. They are the places where time, capital, engineering, and regulation decide how fast domestic gas can become global supply. If one terminal is delayed, the gas does not automatically find another path to the ocean. If a new project takes years, the market cannot treat it like a valve that opens tomorrow. The bottleneck is not a lack of ambition. It is the physical reality of the machine. The clearest way to see a choke point is to watch what happens when one node is disrupted. Freeport LNG is a Texas Gulf Coast export terminal. In 2022, an outage there materially affected U.S. LNG export patterns. That fact is enough. The point is not to dramatize the incident beyond the record. The point is to understand what it revealed. When an LNG terminal goes offline, the gas does not vanish. The wells may still exist. Pipelines may still move gas. Demand overseas may still be there. But the route between domestic gas and seaborne cargo is interrupted. That is the difference between a resource and an export system. A country can have gas in the ground and still be limited by the machinery that turns it into cargo. It can have customers overseas and still be limited by the berths, liquefaction trains, tanks, and loading systems that make shipment possible. This is why a terminal disruption can matter beyond the fence line. It changes flows. It changes schedules. It changes which cargoes can be loaded and when. It can affect how export patterns look even if the wider gas system is still operating. And it shows why redundancy is difficult. An LNG terminal is not a generic warehouse. If a facility is unavailable, another terminal cannot always absorb the impact immediately. Capacity, contracts, shipping slots, pipeline connections, and operating conditions all matter. That does not mean one terminal controls everything. It means each major terminal is a real node in a larger network. The lesson is quieter than a disaster headline, but more useful. America's LNG power depends on specific machines staying available. After Russia's full-scale invasion of Ukraine disrupted European gas supply patterns, Europe became a major destination for U.S. LNG. That made the terminals more visible. Suddenly, the question of how much gas America could ship was not just an industry question. It was tied to factories, heating, storage, shipping, European energy security, and the wider balance of supply. LNG cargoes became part of the way Europe adjusted to a different gas world. But the story should not be reduced to a slogan. U.S. LNG did not single-handedly solve Europe's energy problems. It did not erase geography. It did not make pipelines irrelevant. It did not remove the cost and complexity of moving energy across oceans. What it did was make the export terminal more important. If Europe wants LNG from the United States, the cargo has to begin at a U.S. terminal. If Asian buyers want U.S. LNG, the same is true. Asia remains a major LNG demand region, which means the U.S. LNG story is global, not only European. This matters because the terminal is where domestic abundance becomes a tradable cargo. The buyer may be across the Atlantic. It may be across the Pacific. The contract may be signed in an office far from the Gulf Coast, but the cargo still has to pass through the same kind of coastal machinery. That is why the demand shock did not create the choke point. It exposed it. Europe made the system more visible. Asia keeps it global. The terminals make it physical. An LNG export terminal is powerful because it concentrates so much into one place. That is also why it is sensitive. The same site connects pipelines, industrial equipment, cryogenic storage, ship traffic, workers, nearby waterways, local communities, and export contracts. It is energy infrastructure, port infrastructure, industrial infrastructure, and trade infrastructure at the same time. That is why regulation is part of the story. LNG facilities are regulated for safety, including siting, operations, and hazard review. Export terminals also move through authorization and review processes before they can be built and operated. Those processes do not make the system risk-free. They show that the risks are real enough to require structure. This is not an argument that LNG is uniquely dangerous. It is not an argument that LNG is harmless. The better way to look at it is simpler. These terminals are high-value industrial nodes, and high-value industrial nodes require control. They need inspections. They need procedures. They need trained crews and safety zones. They need to coordinate with waterways and local emergency systems. They need to operate in coastal regions where storms can disrupt ports, power, roads, work schedules, and marine traffic. That is part of the choke point. The terminal has to work technically. It has to work legally. It has to work safely. It has to work in a place where weather and community concerns are not background issues. The more important LNG becomes to global energy, the more attention these coastal plants attract. And the harder it becomes to pretend they are just another piece of industrial scenery. The United States became a major LNG exporter because it built the missing coastal layer. The gas was important. The shale boom mattered. Pipelines mattered. But the global export story depended on the terminals, the places where gas became liquid, liquid became cargo, and cargo became a ship moving out through a channel. That is the choke point. It is not one single dock. It is not one single company. It is not one terminal controlling the entire system. It is a category of infrastructure that is hard to build, hard to replace, and essential to the export chain. Without the terminal, American gas remains mostly a domestic fuel inside a pipeline network. With the terminal, it can become part of European supply, Asian demand, and global energy trade. That transformation is why the machinery matters. When you see an LNG carrier leaving a Gulf Coast terminal, you are not just watching a ship depart. You are watching a domestic resource cross a boundary. Behind that ship are gas fields, pipelines, permits, liquefaction trains, storage tanks, safety systems, berth schedules, tugs, and buyers. The world sees the cargo. The choke point is the machine that made the cargo possible. America can have the gas. The world only sees it after it passes through the terminal.